So we can start straight away. Sorry for the inconvenience. Welcome to the sixth week tutorial session of NPTEL course Power Plant Engineering. My name is Ananthakrishnan. I am a TA. I am the TA of this course. I do this problem solving session as part of my PMRF TA duty. I am a Ph.D candidate from Department of Mechanical Engineering, IIT Delhi. So in this week, we will see a few uh, numericals and multiple choice questions based on nuclear power and solar radiation. Those are the lecture contents for this week. Look into the first problem. So it's the first few problems we will see a few multiple choice questions about the nuclear power. So this is compared to the previous lectures, this will be slightly less in theoretical questions and numerical questions. This will be mostly multiple choice question based session. So have you gone through the problem and identified which out of the four options is the right one? The question is regarding the reflectors of a nuclear reactor. These are made up of boron, cast iron, beryllium, steel. Yeah, the answer is right. The answer is right. The answer is beryllium. So beryllium is a material that is used in making reflectors of a nuclear reactor. So basically, before going and understanding, before actually solving this problem, you should identify what is a reflector and why is it used in a nuclear reactor, and which all are the properties that a reflector require to be used in the nuclear reactor. So one of the most important aspect of the reaction, nuclear reaction that happens in a reactor is that the fuel that they use is very costly. Fuel is expensive, and we should try to actually reduce reduce the fuel and maximize the efficiency. Therefore, one of an additional mount-ons that will be used in nuclear reactor is called a reflector. So what they do, if you consider this as the core, these reflectors uh, is one way by which we can actually reduce the entire size and the fuel requirement. What they do is that they act as moderators and they reflect the leaking neutrons produced back to the core. So the neutrons produced in the nuclear reaction, they will be reflected back by these reflectors to the core. So in a way, they act as a shield that prevents a leakage. So thereby we can make sure that the fuel requirement will be less to produce the same energy. So these acts as moderators are basically the things that slows down the neutrons. Slowing down neutron devices. And usually the materials that will be used as reflectors will be water, graphite, heavy water, and beryllium. So the basic properties of these reflectors are that they are made of scattering materials and they reflect the neutron back to the core. Reflectors will be having scattering materials. So basically graphite powder, water, heavy water, beryllium are examples of that. Look into the second problem. Try to solve it. I'll also try to solve it in a minute. The second question. Right. Option B is right. So the question is regarding the fission chain reactions. Uh, the fission chain reaction is possible when the fission produces the same number of neutrons that are absorbed. Fission produces more neutrons than that are absorbed. Fission produces fewer neutrons that are absorbed. None of the above. The answer is right. The fission produces more neutrons that are absorbed. So basically the neutrons are subatomic particles. These are found in nucleus of an atom along with protons that carry no electric charge. They have a mass slightly greater than that of proton. These are subatomic particles. The answer to this problem is fission produces more neutrons than that are absorbed. So before that, we need to understand what is a fission process. Fission process is a nuclear reaction that can be caused by bombarding high energy alpha particles or protons, neutrons, X-rays, as well as neutrons. However, these neutrons are more suitable for fission. We actually use neutrons rather than the other charged particles to create the fission reactions. And since these are electrically neutral, they require no high kinetic energy to overcome electric repulsion from positively charged nuclei. So once these neutrons bombard a positive charged nuclei, since these are electrically neutral, they do not require a higher kinetic energy to overcome the electrical repulsions. Then what we do is that 2 or 3 neutrons are usually released for each one absorbed in fission. So basically for one absorbed, 2 or 3 neutrons are released. So that is what the problem is in problem has asked for. The fission produces more neutrons and that are absorbed. So we use isotopes like uranium-233, uranium-235, and these are fissioned by neutrons of all energies. Then some other isotopes like uranium-238, thorium-232, these are fissioned by high energy. So I'll try to note it down. The answer to this problem is fission produces more neutrons than that are absorbed. Neutrons are basically subatomic neutral particles in the nucleus of an atom. Their mass will be mostly they have a mass slightly greater than the protons. So what happens in a fission reaction is that usually high energy alpha particles, protons, neutrons, X-rays are used to bombard isotopes. So these neutrons are electrically neutral and require less kinetic energy compared to the other charged particles to overcome the electric repulsions. Therefore, these are preferred. In a fission reaction, uh, In a fission reaction, 203 neutrons are produced. For every bombardment, for every neutron bombarded. Usual isotopes are uranium 238 and uranium 232 and 238. 232, 235, and this requires low. This can be bombarded by low energy neutrons. So basically, the answer to this problem is that fission produces more neutrons than that are absorbed. Look into the third problem. And try to solve. I'll also try to solve. Okay, the question is regarding pressurized water reactor. Uh, in a pressurized water reactor, the coolant water is pressurized to work as a moderator. The coolant water boils in the core of the reactor. The coolant water is pressurized to prevent the boiling of water in the core. No moderator is used. So this is slightly tricky compared to the previous problems. So before actually attending this problem, I'll give a brief background regarding the water reactors available. One is pressurized water reactor, and the second one is a boiler, a water reactor, boiling water reactor. So we actually need to distinguish between these two and see the components of the pressurized water reactor before tackling this problem. So we can start. Just give me a second. Okay, so there are two types of water reactors. One is pressurized water reactor, and the second one is boiling water reactor. So these are used. These both pressurized water reactor and the boiling water reactors, they use light water or normal water as the coolant, and the neutron moderator. Basically, moderator is a device. A moderator is the thing that will be reducing the speed of the neutrons. So they both use uranium as fuel. The previous case, in the previous question, we have seen the isotopes used for producing for the neutron nuclear reaction. So the general structure of both the reactors are quite similar. Uh, they consist of the main components of a nuclear reactor. Those are a containment vessel, a reactor vessel, which houses the reactor core, and a steam generator turbine. So the basic differences between the pressurized and the boiling water reactor lies in the process of steam generation. A pressurized nuclear reactor generates steam indirectly using two water circuits, a primary one and a secondary one. While the boiling water reactor produces steam directly using a single water circuit. So the usually what happens is that the nuclear reactors used for steam generations and electricity productions. One most important factor that needs to be accounted for is the safety. So with the boiling water reactor, uh, the boiling water reactor and in the pressurized water reactor, this is a concern. So since in the boiling water, steam is directly produced by the boiling the water coolant. Uh, the steam is then separated from the remaining water in steam separators positioned above the core and then passed into the turbine. The steam is later condensed just like the normal Rankine cycle and recycled. But in the case of pressurized water reactor, there is a secondary circuit that will be coming in contact with the pressurized liquid. The secondary circuit is then used to uses the heat from the boiling liquid to convert liquid water into steam for the turbine. So this is a second line of defense to prevent any mishap from occurring. So that is the basic difference between the pressurized and the boiling water reactors. Basically, uh, pressurized water reactor and boiling water reactor are pretty similar. They both have, they both use water and water as a coolant and the uranium isotopes as a fuel. So difference is that in the pressurized water reactor, there are two water circuits. The primary circuit, high water will be in high pressure. This heat will be used to heat a secondary water circuit. And then it will be used for this heat in the secondary water circuit will be used for electricity generation. And in the case of boiling water reactor, only a single circuit will be there. Safety is a concern for both. So the question is regarding pressurized water reactor. Here, the coolant water is pressurized to work as a moderator. The question is regarding pressurized water reactor. The coolant water boils in the core of the reactor. The coolant water is pressurized to prevent the boiling of water in the core. No moderator is used. So in the pressurized water reactor, we have seen there are two water circuits. So moderator is something. So as I tried to explain in one of the earlier discussions, moderator is something that slows down the neutrons produced during fusion, making them more likely to cause further fission reactions. So the moderator is a material used in nuclear reactors that will reduce the speed of the neutron produced. And what it does is that it will allow the neutrons to produce energy even further. So water in a pressurized water reactor, the coolant water is actually pressurized. So what happens is that once the water is pressurized, as you would have seen in the LPG, in order to transport it from one place to another, the LPG, the petroleum gas is liquefied under high pressure. Just similar to that, water will be pressurized. Once it is pressurized, it will chances of it staying in the water state is very high, even at a higher temperatures. So water is pressurized to maintain its liquid state. So this allows high temperature. This allows, since water is in the liquid state, high temperature in the reactor can be nullified because it can be taken. It can be taken as a specific heat of water is higher in the liquid state compared to the gaseous state. Cp water in the liquid state is higher compared to Cp gas. So once the Cp is high, the amount of energy that can be stored in the water is also high. So the energy transferred to water can also be high. So this ensures a better efficient energy heat transfer process. So that's why water is pressurized in a pressurized water reactor. So there is a secondary water loop that will be taking the heat from this pressurized water, and that will be delivered to the that will be used for electricity generation, for heating of water and then further producing steam generation for the electricity generation. But then the question remains whether the cooling water is pressurized to work as a moderator. Cooling water boils in the core of the reactor. Cooling water is pressurized to prevent the boiling of water. So these are counterintuitive. Cooling water, it is pressurized to prevent the boiling of water to remain in the liquid state. So this is wrong. It is pressurized to prevent the boiling. Wrong. No, water is used as a this water coolant water is pressurized to work as a moderator. This is right. Moderator is anything that will be reducing the speed of the neutron, and it will allow the neutron to produce more energy further by producing even more fission. So here pressurized water is pressurized to remain in the liquid form to take more energy will act as a moderator as well. So answer to the question is option A. Look into the fourth problem. This is a continuation of the previous problem. Yes, the function of moderator in a reaction is to reduce the speed of the neutron. Yeah, to allow more fission reaction to happen. Yes, yes. Look into the fifth problem. And also try to solve within a minute. Yes, right. Answer is equal to unity. When a nuclear reactor is operating at a constant power, the multiplication factor is less than unity, greater than unity, equal to unity, none of the above. So the multiplication factor is nothing but reproduction factor. It's the ratio of the number of neutrons produced in one generation to the neutrons produced in the preceding generations. So as the name suggests, if the number of neutrons produced remains the same in different steps or different generations, is the same, then the power produced corresponding to the neutron production is also the same. The energy transfer will be same and the power produced will also be the same. So the reproduction factor or the multiplication factor equal to the number of neutrons produced in one generation to the number of neutrons produced in the preceding generation. If this ratio is equal to 1, that means that the number of neutrons will be the same in the consequent in the consecutive steps, and this will be resulting in the same power, constant power. The answer is equal to 2 meter. Look into the sixth problem. Okay, but the question is regarding the conversion ratio of a breeder reactor. Whether it is equal to unity, more than unity, less than unity, none of the above. So compared to the previous one, reproduction or multiplication factor, this is slightly different. This is basically how many number of, this is something that relates the number of neutrons bombarding a material and the number of fissile atoms produced. Basically, the conversion ratio is the ratio of new fissile atoms produced to the fissile atoms consumed. Fast breeder reactor uses fast neutrons. Fast in the sense it will be unmoderated to breed fissile plutonium and possibly higher transuranic from fertile uranium-238. The fast spectrum is flexible enough that you can also breed fissile uranium-233 from thorium. One measure of a uranium, one measure of this reactor's performance is conversion ratio. So the conversion ratio is the ratio of new fissile atoms produced to fissile atoms consumed. A breeder reactor is a nuclear reactor that generates more fissile material than it consumes. The ratio of the fissile material produced should be greater than the consumed. So this breeder reactor is the one where the fissile, the fissile atoms produced will be greater than consumed. So that's why it's called breeder reactor. So the conversion ratio when used for a breeder reactor will be greater than 1. So the conversion ratio in the case of a breeder reactor is called breeding ratio. So the answer is correct. It's greater than 1, more than unity. Look into the numerical. You have to determine the mass defect and binding energy per nucleon of oxygen given the atomic mass units of proton, neutrons, electrons, and atomic mass of oxygen is also given. It's a small numerical. Yes, mass defect is correct. So I'll try to solve this. So the question is regarding mass defect and a binding energy per nucleon of oxygen. So we have to actually tackle this problem using the equations. So in this case, the first question, the first part of the problem, we have to determine the mass defect, delta M. So it's being given the atomic mass unit of proton, neutron, and electron as 1.0, these three. So in case of oxygen, 8 oxygen will be having its atomic number 8. So we have to multiply it with 8, these three components, protons, neutrons, and electrons. And then we have to subtract the actual mass of atomic mass of O2, oxygen 16. So that will be giving the mass defect. Basically, the atomic mass of O2 is 15.99491. But from the mass of the proton, neutron, and electron, there will be a difference. So that is what is called mass defect. So what we could do is we multiply 8 into protons, neutrons, and electrons. So that is 1.007. Yes. So that will also fall into the total mass. Electron mass is also included, minus the atomic mass of oxygen, 16. So these three will give the value of 0.130701 atomic mass unit. So once we get this mass defect, binding energy is quite easy. So binding energy equal to this mass defect delta M into the energy equivalent of 1 AMU of mass. Energy equivalent of 1 AMU of mass. So this we know, that is 0.1307. How to calculate this one? This will be equal to basically mv squared term. So one basically delta E is equal to mc squared. So we have to consider the speed of light, velocity of light as 3 into 10 power 8, and one atomic mass unit. You have to determine what is its that is a unit, 1 AMU. What is its conversion to a kilogram? So that will give uh, the uh, the total binding energy. So this delta M is in terms of AMU. So energy equivalent in terms of for the one AMU of mass is this is equal to E is equal to delta MC squared. So here this will be 1 AMU. The mass will be in terms of kilogram. So that is 1.66 into 10 power minus 27 kilogram multiplied by 3 into 10 power 8 meter per second squared. So this term will be equal to 931 meter EV. So we have to determine the binding energy, actual binding energy. So that will be equal to 0.13701 multiplied by 931 mega EV. So once you get that, you just multiply and you'll get it as 127.6 MeV. The question is a question in this problem is binding energy per neutron per nucleon. So nucleon is combination of neutron and proton. So binding energy will be equal to this 127.6 divided by 16. 8. There are 2 8s. So it will result in 7.97 MeV. So basically what we have done is that we have calculated the mass defect from used to bind the mass defect used to bind the protons, neutrons, electrons into an oxygen O2 molecule. Here there will be 8 protons, 8 electrons, and 8 neutrons. So that will be the initial one. And then we subtract it with the atomic mass given AMU in terms of AMU, and we'll get the mass defect. So we multiply with the mass defect into energy equivalent of 1 AMU to get the binding energy. So mass defect is in terms of AMU. So the energy, this is mega electron volt in terms of mega electron volt will be given as 1.66 into 10 power minus 27 into 3 into 10 power 8. So this will be equal to 931 mega electron volt. So 1 mega electron volt will be equal to 1.6 into 10 power minus 13 joules. So this unit, this is a conversion to mega electron volt. This will be quite low. Therefore, in terms of MeV, we'll get it to be around 931. We multiply with the MU, we'll get the total binding energy. And in terms of mega electron volt, you have to multiply it with this conversion factor to get in the energy in terms of joules. binding energy per nucleon will be equal to, you have to divide it by the sum of protons and neutrons inside the nuclei, and that will be 7.97 mega electron volt. Look into this problem. So till now we have seen problems related to nuclear radiation. And now from now onwards, we'll see a few on solar radiations. Right. The total radiation emitted and reflected from a surface is called irradiance, irradiation, radiosity, intensity. So it's straightforward one. It's radiosity. It's a combination of uh, emitted and the reflected radiation. So irradiance. So before that, we have to individually look into the terms. What all are they dealing with? So, uh, so we have seen that the total radiation emitted and reflected from a surface is called radiosity. Then, basically, if you take a surface, you have to look into the a bit of radiation can come and get absorbed into the material, and a portion of that can transmit to, and remaining portion can reflect. The reflected portion is denoted by rho. Absorbed portion is called alpha, and the transmitted portion is called tau. So the total alpha plus rho plus tau should be equal to 1. So the quantity asked in this problem is reducibility. What is reducibility? There is this reflected portion, and in a steady state heat transfer Kirchhoff law application, alpha will be equal to epsilon. That is the absorb any component that the component of the irradiation that is absorbed, that will be equal to the emitted component. So that is the L epsilon part, emitted component. So the combination of this rho plus epsilon is called this emissive power. This is emissive power, and then this is the reflected portion. These two combination is called radiosity. Then the first part is irradiation, and the second one is the first is irradiance, and the second one is irradiation. So irradiance is actually the instantaneous power of radiation falling on a unit area. So basically, watt per meter squared, and that is instantaneous. Irradiation is the total energy received per unit area over a period, over a specific period. So energy per unit area. This is joule per meter squared. And last one, intensity of any quantity could be energy or anything. It could be represented as watt per meter squared. It can be any quantity. It can be solar radiation. It can be any other radiations as well. So basically, the first two quantities can be slightly tricky: irradiance and irradiation. Irradiance is an instantaneous quantity in terms of watt per meter squared, and irradiance is averaged out over a period in terms of joule per meter squared. The answer to this problem is radiosity. It's a total radiation emitted and reflected from a surface. Yes, answer is right. Answer is January. The Earth revolves around the Sun in an elliptical orbit. In which month the Earth is nearest to the Sun? Is it in January, March, July, or December? So, the orbit of Earth around Sun is elliptical in nature, but the distances of these points will not be equal at both these locations. So, in case of January, it will be at the closest. The It's called perihelion, and in July it will be farthest. It's called a aphelion. The aphelion distance is 152.1 million kilometers, and perihelion is 147.1 million kilometers. So in January, the southern hemisphere experiences harsh summers, while the northern hemisphere will be having slight winter. In the July, the northern hemisphere experiences harsh summers, while the southern hemisphere will be having winters. So the difference is slight, about 5 million kilometers compared to the actual distance. It was kind of, this question is not purely theoretical, it's just an informative question. Look into the 10th problem. Yeah, some of you got it correctly. The answer is solar energy to thermal energy. Uh, we are actually not dealing with photovoltaic cells. We are actually dealing with solar collectors. The function of a solar collector is to convert the solar energy into thermal energy. Right. Uh, the PV cells convert them to electricity. Here, some kind of the heat will be transferred to some kind of a heat transfer fluid that can be, depending upon the applications, it can be liquid sodium. or it can be water in certain cases. So the answer is solar energy into thermal energy. So this is the last part of this session. I'll discuss about the various angles associated with solar radiation. So this is kind of an explanation for the various angles. So this is in this one you need not do anything on your own. I'll try to explain the various angles that are associated with solar radiation. So I'll try to draw the schematic first and then uh, note and explain the angles one by one. So take a 2D representation of the our globe, and there will be a slight tilt between the north and the southern poles. This is the equator. The expect sun to be somewhere here. The solar radiation comes in this direction. This is the center point. So this is the actual axis, north-south axis. It rotates around in counterclockwise direction. Yes. So the first angle is lambda. So the longitude I'll try to denote by a different, I depict by a different color. Starts from here. So like this, take a location somewhere here. and we will connect it from the center point. So this angle lambda at some so this is on the surface of the globe at some locations, at some arbitrary location. This is the meridian from the north-south direction. So I'm drawing it only till the equator point. And from that point, we take an angle. That is one angle is lambda, and to make it a bit more clear, this can be slightly tricky. I'll make it a 2D image. So just like the previous case. This is the anti-clockwise direction, and there is its locations. There's this particular location where the sunrise fall. And its angle from the equator is denoted as a dotted line, and its angle from the equator is represented as lambda. And from the central line, there is another angle called delta. I'll clearly explain which all are these angles, delta. And then this angle is called a lambda minus delta. So lambda is called a latitude angle. Delta is called a declination angle. And in this one, there is another angle called hour angle. Omega is called hour angle. Here, this is O. O is the center of Earth. North N is the North Pole. This is the South Pole. And this is the point P. The point under consideration, point on the surface of Earth. Point on Earth, an arbitrary point on Earth. So what we have on our hand is three angles. One is lambda latitude angle. The second one is delta declination angle. The third one, hour angle. The latitude angle is defined as the angular distance of the point P north or south of the equator. So how much is the angle from the equator? So at the equator, it will be 0 degree. And if we move to the pole north or south, it will be 90 degree. So lambda is the angular distance of the point P from the equator. For example, so Earth, India lies between 8 degree and 32 degree, or north from the equator. So southern tip of the India lies at a latitude angle of 8 degree, and northern tip lies somewhere around 32 degrees north. So it falls in the tropical region. That is called a lambda latitude angle. The second one is called the declination angle, delta. So the delta is defined as the declination angle. So the relative angle to the equal. So this declination angle is actually calculated with respect to the relative angle from the equatorial plane. So it's not that straightforward. Depending upon solar position, sun's position, this declination angle will keep on varying based on a different time of year. So this is not a real angle as such. Delta, the declination angle, is not a real angle. For solar energy calculations, so we use coordinates fixed in the earth as if the sun moved around the earth. Considering the geometry of the point of the view of the earth, the sun traverses from one circular orbit around the earth on each day. In general, this orbit does not lie in the plane of the equator. Rather, so the sun, the rotation of sun around earth rather than uh, earth rotating around sun only for solar energy calculations is determined in terms of delta. So how much will be the this orbit where the sun moves around earth is not around the equator. It will be slightly varying depending upon the position where we are on a particular year. So it need not be moving sun. In reality, earth will be moving around the sun, but uh, uh, for just for the calculation purpose, we assume that sun moves around the earth and it doesn't move around the circle. It actually moves, the sun's radiation moves in different patterns depending upon the time of the year. For example, uh, towards summer in the northern hemisphere, we feel that sun will be towards the northern hemisphere, northern part of the globe. When it is summer in the southern hemisphere, we feel that sun will be rotating around the southern part of the globe. So depending upon the time of the year, the angle at which the sun's radiation comes varies. So to represent that, we define an angle called solar declination angle. The So it is calculated based on the line from the sun to earth uh, at point of the year and that point of the year with respect to the equatorial plane. So in this one, this is called a delta, and some part of the year, the sun will be at an angle, it will make an angle delta with respect to the center. So the this is a declination angle, and the third one is called hour angle. So hour angle is also it's a very straightforward quantity. It is the angle measured in the Earth's equatorial plane between the uh, projection of this point OP along the equatorial plane and the projection of a line extending from the center of the sun to the center of the earth. So this is the angle between this point and the projection of the point OP to the equatorial plane. So this OP will be projected onto the equatorial plane like this, And then depending upon the time of the day, the solar radiation will be moving around this equatorial plane. So the angle between these 2 points, this line will be fixed and this line will be varying. So at any point, this angle, our angle, will be given. It varies from 0 to 360 degree. So this is our angle. It is angle measured in the Earth's equatorial plane between the projected OP and the projection of a line from center of sun to center of Earth. So the hour angle at any location is given in terms of solar noon. Solar noon will not be the same as that of the actual noon. The noon in terms of 12 o'clock, you do not expect the sun's radiation to come directly on top of the person. So there can be a certain time in the day where the sun's radiation will come directly on top of a person, or in certain cases at an angle. So you do not expect the sun to directly come on top if you move away from the equator, but there will be a certain time of the day where the sun will be at its topmost position uh, compared to any other time. So that is called the solar noon. That will not coincide with the time noon of 12. So certain locations it can coincide. That will be pure coincidence, but in other locations it may not. So that is the third angle, our angle omega. It is measured between the projected point on the equator of a particular position P. This P will be take this case P should be somewhere around India, and if you project it along to the equatorial plane, it will come somewhere here, and the angle the solar radiation will make by time of the day, that will be our angle theta. Depending upon certain cases, the hour angle solar the solar noon will be actually the time where the hour angle is 0. Our angle is exactly 0, and it won't coincide with the actual noon. So this is that when the hour angle becomes equal to 0, that is called solar noon, and it is not equal to the actual time noon. And declination angle is with respect to different time of the year, how the solar radiation will fall at various points of the year at different locations. And then lambda is the latitude angle that is measured with respect to the equator. As we move further north, it will be 90 at the north pole, and it will be plus 90 or minus 90 depending upon the angle notations that we take. That finishes the session for today. Here we have seen a few multiple choice questions based on nuclear radiations, nuclear power, and one numerical as well, and couple of multiple choice questions and one explanation video on the solar angles with respect to the solar radiation. So in the solar angles, we have discussed latitude angle, declination angle, and hour angle. So in this next week, we will see a bit more on solar thermal power, wind energy, wave and geothermal energy, photovoltaic conversion, and a few numericals based on these as well. That's all for this session. Thank you. And we'll meet next week at the same time.